Yeah. What? I think everything. To say that x equals 5 equals 2x. Yes, 2 values. So basically, ultimately, mathematics is the study of stated that are either so try to make us think of the math.
All right, folks, wrap up your conversations. Let's review as a group. And if you don't already have your name tag out, will you please put your name tag? That way I can keep on learning all of your names. So let's start with the first question. Approximately when was the technology of algebra written down for the first time ever? Daniel? It was a long time ago. It was a long time ago. A little more specific, Nick? Someone like to help? With the volunteer, the answer? When was it? It wasn't 1980, no.
Are we powerful? Can we get it?
It was over 1,000 years ago. It was on the algebra overview that we did on the very first page. If you have that algebra overview on the very first page. On the first page at the bottom. Wait, did we not do this? Oh, maybe we didn't do this. Maybe that's why you don't have this answer. Folks, algebra started off in yeah, we didn't do this. It was 820 AD. Sorry, okay, that was silly of me. We didn't do that activity together. I'm sorry, I was thinking someone else. So yeah, 820 AD. Can you believe it? So in 820 AD, that was when the technology called algebra was invented and written about on planet Earth. So if you want to go back and say, when did algebra begin? It was in 820 AD. So that's 1,200 years ago that people have been using algebra to solve math problems. Okay, so that problem probably caught you all off guard. Okay, 2. In order for a math problem to be algebra, what 2 symbols do you need to see? For instance, I'll give you an algebra problem right here. I'm going to do 3x plus 7, maybe? Yeah, is 31. So what symbols need to be in the problem for it to be an algebra problem? Matthew, did you want to volunteer?
One of them is certainly an equal sign.
Equal sign for sure. There has to be an equal sign. And one other symbol. Yes, go ahead, Emily.
Variable?
Yeah, a variable. You need a variable and an equal sign. So if you don't have a variable and an equal sign, it's not an algebra problem. So for instance, if I wrote down 5 plus 2 equals 7, well, no, because you're not solving for x. It's just a true statement, right? Whereas if I were to write down 4x minus 3, is that an algebra problem?
No, it's an expression.
Yeah, it's just an expression. It's just an expression. There's no equal sign, so you can't possibly solve for x right here. All you can really do here is plug numbers in for x, but it's not an equation, so you're not really saying it's true or false. Okay, so that's what a math problem needs to be algebra. What does it mean to say x equals 5 in the equation 2x minus 7 equals 3? First of all, is x equals 5 the correct answer?
Yeah.
Right, so how are you sure that x equals 5 is the right answer? Yeah, you plug it in, and what happens, Emily?
Well, you just plug it in.
You plug it in, and then what? And then you solve for it? Well, what happens when I do plug it in? I have 2, and then I plug in a 5, minus 7 equals 3. So 2 times 5 is 10. 10 minus 7 is 3. And so what do we end up with?
3.
It's just a true statement. That's it. When you get to the correct answer in algebra, you should be able to plug it in, and it will make a true statement. That's it. What would have happened had I plugged in any number other than 5?
Be untrue.
Yeah, it would have been untrue. It would have been false. Choose a number for us, Crystal. Just pick any other number.
6.
6. If I had plugged in 6, 2 times 6 minus 7 equals 3. That would have been 12 minus 7 equals 3, which is 5 equals 3, which is false. That's not true at all. It's false. So anytime someone wants to walk up to you and claim that x equals 5, or x equals negative 13, or x equals 100, they're claiming that they have found the number that you can plug into the equation to make it true. And this gives you a really easy way to check their answer. You know, someone comes up to you and they say the answer is negative 13, but you don't have to take their word for it, right? You can go ahead and just plug it into the equation and see if it's true or see if it's false. And so it's never a guessing game. You can always know immediately if you have the right answer or not. Okay, so yes, what does it mean to say that x equals 5 is the answer? It means if you plug it into the equation, it will make the equation true. That's our mantra for the whole class. If you plug it into the equation, it should make the equation true. Okay, ultimately, mathematics is the study of statements that are either, I heard it, true or false. Exactly right. We're studying statements that are either true or false. Just like this one became true, and that's what made x equals 5 the answer. Or this one became false, and that's what made x equals 6 not the answer. So ultimately, when we study mathematics, we're actually studying equations that are either true or false. But everything we do in this class is going to boil down to, is it true or is it false? Everything we do, true, false. Okay, what is the basic rule of algebra? So for instance, when I have this equation right here and I'd like to solve it, you can do anything you want. Can I really do anything I want? What can I do right now to start solving this problem?
Subtract 7.
Subtract 7, right? So if I do subtract 7, do I just do it right here? No, you have to do it to both sides. And that's the rule. You can do anything you want in algebra, anything at all, but you have to do it to both sides, right? So if I did subtract 7 from both sides, that would be a very convenient thing to do because it cancels that 7, and my equation becomes simpler, and I get one step closer to the answer. But that just happened to be the convenient thing to do. Could I really do anything I want? What if I took that same first equation, 3x plus 7 equals 31? Could I go ahead and add 20 to both sides? Am I allowed to? I'm allowed to. Sure I am. I can. Would that be very beneficial? No, now I'd have 3x plus 27 equals 51. Did that help? No, it didn't really help. It didn't take me any closer to the answer, did it? But was I allowed to do it? Yeah. Yeah, absolutely. You can do anything you want so long as you do it to both sides. The reason we do particular things like what should I do right now? What should I do? Subtract 27, right? And why is subtracting 27 the right thing to do? Because it cancels out this term. And it does, in fact, make this equation simpler, and it gets me one step closer to my answer. Now what should I do? Divide by 3, right? Because that takes me one step closer to my answer, which is x equals 8. Is x equal to 8? Yeah, how do we check?
Evaluate.
Yeah, I plug that right back into the beginning, right? So if I plug in 8, 3 times 8 is 24, and 24 plus 7 is 31. So indeed, if I plug it in, I get 31 equals 31. And what is that thing? True. Does the 31 matter? Does it matter that it's 31 equals 31? Like, is there something special about the number 31? No, nothing at all. There's nothing special. What's special is the fact that it's true. Okay, so 31 is not what x is equal to. X is equal to 8, because if I plug in 8, it makes the equation true. 31 just happens to be the arbitrary number that happens to be in the true statement. And that's it. Okay, finally, when looking at algebraic work, you should be able to clearly see the problem being solved, from top to bottom, alternating between lines of what? This might not have been very obvious. I'm going to start with this problem, okay? So I had the 3x plus 7 equals 31, then I subtracted 7 from both sides, and then I have 3x equals 24, and then I divide by 3 on both sides, and then I get x equals 8. What am I alternating between? What's the first thing that you see here? It's just an equation, right? And then what would you call this when you do the same thing to both sides? Maybe we have a shared vocabulary for this or not. I just call it an action step, right? Like this is my action step. I subtracted 7 from both sides, and then I had another equation, 3x equals 24, and then I had another action step on both sides, and then I had another equation. So that's it. In algebra, when you're looking at proper algebra, you should see it go equation, action step, equation, action step, equation, and you just keep going like that until you get to your answer. That's what proper algebra looks like, and that's what I'll be showing up on the board. What do you notice? What else do you notice as a telltale sign of algebra? Yeah, I'm bringing down the equal sign to be sure. The equal sign should be nice and stacked on top of each other. What else is a telltale sign of algebra that you should always see in every algebra problem? Sure, the x has to be there because we're solving for it. What do you always have to see in every algebra problem? You should see cancellation lines. You should see cancellation lines because that's what you're doing in every step of algebra. You're canceling something, right? I started off by wanting to cancel the 7, so I canceled the 7. And then I wanted to cancel the 3, so I canceled the 3. And so on. So when you do algebra, it should be alternating lines of equation, action step, cancellation. Equation, action step, cancellation, and equation, and so on. Those are proper algebra. All right, well, wonderful, folks. I realize now, because we didn't do that particular activity together, those questions might have been a little out there. I will make sure that the questions are a little more honed in next time. I apologize for that. But that was still a good overview of what algebra should look like. So today, where are we? Today is this 22nd, right? So we have today to cover sections 5.1 to 5.3, which we just barely started last time. And then on Wednesday, we'll do 5.4 to 5.6, at which point I will be collecting your midway quiz. I'm going to give you a midway quiz today, which will cover just the material that we covered in class today. And then you have until next class period to bring it back to me. It's just one piece of paper, front and back. You just do it yourself. You can use your notes. You can use your textbook. You just can't use another human or Google. Okay, and then next week we'll do chapter 11, and then the week after that you'll take your test on chapter 5 and 11. So I'm just letting us all know where we are and where we're going. Notes. Today I will give you your first midway quiz at the end of class. So at the end of class I'll give that out to you folks. And then, of course, I'm going to start every class with a joke. So I have a joke for you folks. The joke starts, there were 30 cows. There were 30 cows in a field and 28 chickens. How many didn't? If you know the answer, don't say it. There were 30 cows in a field and 28 chickens. How many didn't? Who didn't? That's a very good question, Deegan. How many didn't what? I'm going to say it one more time. There were 30 cows in a field and 28 chickens. How many didn't? This is a really good riddle. You're going to tell this at the next party you go to, I know. Okay, you guys ready for the answer? Should you wait, or should I wait until the end of class? Say it now? Okay, here we go. There were 30 cows and 28 chickens. How many didn't? 10. Right, so there were 30 cows and 28 chickens. So how many didn't? 10. 10 cows did not eat chickens. Yeah, pretty crazy joke, right? I guess that's more of a riddle than a joke, but it's a good one. So I know you're all going to go home and tell that to your friends today. Super. So here we go, folks. Where were we the last time? We just had started section 5. Oh, sorry. Let's go over two things real quick before we get into material. Syllabus quiz and my math lab. So the syllabus quiz, did I collect that from you yet? No. Okay, good. So let's talk about it first, and then I'm going to show you my math lab so you all are looking at the same thing, and then we'll start the material. So the syllabus quiz. This is when I'm just going to call on everybody for the answers. So starting from the beginning, I need to bring a what to every class? Vanessa?
I mean, I put
Calculator, yes, absolutely. I mean, there's a lot of things you need to bring to every class, folks, but you need to bring a calculator to every class because whenever I say type it into your calculator, I say everybody to type it into your calculator. Okay, how about by the first week of class, I need to purchase online access to what, Jesus? Yeah, my math lab, and I'm going to show that to you folks in just a second, my math lab. Notes packet, the 5% notes packet. The packet is worth 10 points, and I will lose what for every problem I leave blank or that I don't do, Jackie? Yeah, 1 point. So it's only worth 10 points, and you lose a point for every problem you leave blank. So of course, none of you are going to leave anything blank, right? You'll fill in the whole packet. What about 5% midway quizzes? On my honor, I must complete it on my own. I can use blank, but I can't use blank. How about David? Yeah, you can use your books and notes. Yeah, you can't use another human, and you can't use Google. Okay, practice test. The practice test is worth 10 points, and I'll lose what, Deegan? 30%. Oh, wait. The practice test. Yeah, you lose 1 point for every problem you leave blank. So again, don't leave anything blank. 25% my math lab. This wasn't on the syllabus, was it? It was not on the syllabus. I apologize for that. Everyone, the answer is that the My Math Lab homework is always due on the day of the test, but if you don't finish it by the day of the test, you can continue working on it for a 30% deduction. That is on just the problems that you didn't do on time, right? So everything you finished on time, you get full credit for. But if you had some problems that you didn't finish by the day of the test, you can keep working on them the next day and the next day and the next day. But you're only going to get, you'll get 30% off for the ones that you do them late. Okay? And that's because I still want you to finish. I think it's a really important idea that you all finish all the homework online. Even if you're late, you should still go back and finish it, because that will help you study for the final exam, and it will help you prepare for the chapters that come later. But I have to take some sort of deduction because it's not fair for the people who finished on time. If they finished on time, they get full credit. If you do some late, you lose 30%. Okay, 40% tests. If you have an emergency or sickness on the day of the test, you must email Mr. G when, Eduardo? Oh, within 24 hours. Is that what I said in the syllabus? I feel like I said something else, Vanessa. What did I say? Before class. It just has to be before class. Yeah. Within 24 hours would be too late. Like if we took a test today, and then like later tonight, you're like, oh, Mr. G, I wasn't there. I'm like, yeah, I know. So that's too late. You have to tell me before class. Okay, thank you, Eduardo. Thank you, Vanessa. Okay, final exam. I'll keep all of my blanks and review them. Emma? The 20% final exam. You'll keep all your
Quizzes, tests.
Yeah, all of your quizzes and tests. You should definitely keep all of those and review them beforehand. Okay, attendance. I will sign in and be in my seat at the start of class, which starts at? Yeah, 12:30, right? Were we all here at 12:30? I think we were all here at 12:30. That's right. I'm allowed up to 2 tardies for free. Starting with the 3rd tardie, I will lose blank. Ingrid? Yeah, 1% off the top of your grade. So your final grade for the whole class, I'll take 1% off for every tardie after the 2nd tardie. I'm allowed up to 2 absences for free. Starting with the 3rd absence, I will lose blank. Chris?
1%.
Yeah, another 1%, right up the top of your final course grade. So, folks, please always be here on time and never miss class, even if you're not feeling very well. Like, even if you're like sneezing and not feeling well, come to class anyway. We'll just make you sit in the back, right? Because we don't want to get sick. But you come to class anyway. All right. I can be absent a maximum of 5 times, excused or unexcused. And on my 6th absence, I will be done. Yeah, withdrawn. Not emotionally withdrawn. I mean, you might also be emotionally withdrawn, but you'll be withdrawn from the class. That's the key. Okay, I can earn extra credit for perfect attendance. If I have 0 tardies, I earn what? Isn't you get 5 bonus points on the final exam. And if you have 0 absences, you get what? Jasmine? This Jasmine? Didn't we? You have 5 more bonus points on the final exam. Okay. Required office hours before the day of what? Crystal? Yeah, the first test. Just the first test. Our first test, I just showed it on the board. It's like 2 weeks from now. Before the day of the first test, I will come into office hours with Mr. G for like a 5-minute chat to review notes and homework. If not, what will you lose? Genesis? Yeah, 50% off your first exam. Now, folks, I told you that's just a scare tactic, right? I don't want to do that to any of you. I want you to come into my office hours. Some of you already came in. How long did it take? Yeah, 2 minutes maybe, 3 minutes maybe. So I mean, just come on in, we'll go through your notes and say hi to each other, and then that's it, you can go. Okay, if I earn less than what on any quiz or test, yeah, 70%. 70% is the cutoff. If you get a 70%, you're good to go. You don't have to come in and see me. But if you get a 69% or less, you need to come into my office, and we're going to go over every single question on the test. I'll record your grade initially as a 0 until you come in and actually review the test with me, and then I'll put your grade in. Okay, and then you sign it and you date it. So how about at the end of class, you can drop that off right up here. Don't take everyone's off right now. Just we'll do that later. All right, thank you, folks. Now, my math lab. Oh, I also want the student information sheet. So at the end of class, everybody will bring up the student information sheet and the syllabus. Thank you. So, folks, my math lab, which I think a lot of you already have access to. In fact, most of you. So you go to the website, My Math Lab, you click sign in. Sign in. This is what your sign in looks like. Password. Okay, now I have a lot of classes I'm in, but you just have one class you're in, which is what, Mat 120? So Mat 120, you click on that one. And then, what is the only button that you guys have to click on? Homework. Right here where it says homework. So you click on homework over here, And the way you'll know for sure that this is you is that it only has the chapters we're doing. In this class, we're only doing chapters 5, 6, 7, 9, 10, and 11. Technically, we're doing chapter 5 and 11 together. I don't know why 11 bumped all the way to the bottom. You can see that chapter 5 and 11 both have the same due date, which is February 5th. So 5 and 11 go first, and then you'll go in order of 6, 7, 9, and 10. So those are your only homework assignments. I'll go ahead and click on chapter 5 real quick. When you click on it, it will show you all the questions, which there are 57 questions total. And then I go ahead and click on the first one, question 1. It will give you a pop-up window. And it normally takes, I don't know, 30 seconds to load the first window. But then after that, it's very quick from one question to the next question to the next question. So you can hum or sing to yourself while you're waiting. Here's the first question. It says, combine like terms, write the result with descending power. So what's negative 5y squared plus 7y squared? 2y squared, right? Because negative 5 plus 7 is 2. So answer A, the polynomial cannot be simplified. That's not true. It can be simplified. We just did. The polynomial can be simplified, and the answer is 2y. And how do you make an exponent? Yeah, down here at the bottom, you have all these nice little buttons for a fraction, a mixed fraction, an exponent, absolute value, square root, a third cube root or fourth root, a subscript, a parenthesis, and more. You can click more. There's a ton of other buttons down there for typing in your answers. So I'm going to go ahead and type in squared. Uh-oh, where did it go? Oh, there it is. Oh, that's true. You could always use a caret button, but I'm going to use the exponent button, 2y squared. So now that I have done that, I'm going to click check answer. Nice work, it tells me. Isn't that nice? So then I click next question, and away we go on to the next question. So I think from that question, you can tell that not all these questions are very long. It could just take a matter of seconds for you to think of the answer and type it in. So about this one, 0.7x cubed minus 0.4x. Can that be simplified? No, because the exponents are different. That's an x cubed, and that's an x. So they cannot be combined. I'm going to say the polynomial cannot be simplified. Wait, that's can be. Sorry. Polynomial cannot be simplified. Oh, but the polynomial written in descending powers is. So even though I can't simplify it, they want me to type it in the order of descending powers. So I'm going to do 0.7x cubed minus 0.4x. And let's see how I did. Check the answer. Oh, good. Nice work. Okay. So this is the basic flow of my math lab. You go in and you just start answering the questions. Now, what if you're not sure how to answer the question? What do? Yeah, you go on question help. Now, the first thing you can do is cry. But don't. I don't think you should cry. You should just click on question help. Question help is very helpful. Look at this. Under question help, the very first one is help me solve this. And it will just go ahead and walk you through the answer, the actual answer. So if you click help me solve this, it pops up a little pop-up window. Yep. And it's going to literally show you how to solve the problem step by step by step. The thing is, if you choose show me how to solve it, it's going to give you a different problem to then solve for credit. Or you can click on view an example. If you click view an example, it will show you a different problem and walk you through it step by step by step. So those are two really good options right there. Or you can click on this animation link. It'll show you how to solve the problem like a little video. Some of them have a video. You can also click on the textbook, and that will show you the appropriate section of the textbook that taught that material. Or you can click Ask My Instructor, and then it will send an email straight to me. And I'll get the email, and I'll respond right back to you. So by all means, I would encourage you to look at the Help Me Solve This and do an example first. But then if those don't help, you can always email me, and I'll help you via email. Okay? Okay, well, that's it. That's you working your way through the homework. So now I'm going to go ahead and close that. You're sure? Yes, I'm sure. And now you can see my little grade book here. Yeah, there we go. You can see I've already done question 1, little green check mark. I've done question 2, but I have not yet done question 3. Now, it shows here that I got question 3 wrong. Can I try it again? Yes. Yeah, you can try it as many times as you like. You can try it over and over and over again until you get the right answer. So ideally, you should get all of these problems correct and not leave any with a little red X next to it. Okay. Well, what else is there to tell you? If you click anywhere else besides homework, which just shows the 6 chapters that we're doing in this class, like for instance, I think quite a few students clicked on quizzes and tests, and they saw all this, and they were like, oh no, do I have to do all that? No, you don't. You don't have to do any of that. This is just other stuff that my math lab happens to have. We're only doing the homework for the chapters that we're covering. Okay. Folks, what questions do you have about my math lab? Great question. How do you get to the textbook? Well, on the one hand, from within one of these questions, it'll take another second to just pop-up window to pop up. But when you go over here to the right to question help, it's right there, textbook. So when you click on textbook, it will take you, oh, it blocked. Don't block. Oh, there. It'll give you a pop-up and it will take you to the textbook, to the page of that material. So that's one option. You can click on that to get to the textbook. The other option, if you look over here, right here, you have chapter contents. So down, oh, did everyone see it before I clicked on it? Chapter contents, over on the left-hand side. So we click on homework to get to homework, but if you want, go straight down to chapter contents. And these are all the chapters of the book. So what are we starting with? Chapter 5. So you click on that, we're in chapter section 5.1, so you click on that. And then right over here, it says view the multimedia e-text. And then when you click on that, it will show you, it'll pop up a window and take you to the book. It says Pearson requires Adobe Flash. So you might have to make sure that all of your web browsers are working properly. Oh, here we go. It's totally working. So again, it takes probably 30 seconds for anything to load the first time, but after that, it loads pretty quickly. That was you, Lily. Did that answer your question?
Yeah.
Okay. Who else has a question about my math lab? Yes, Emily.
So are we just going to do homework and not?
Right, just
so
homework.
No quizzes or testing?
Right, you'll test here in class, and the only quiz you take is the midway quiz, which you take home with you, do it on your own, and then bring it back to you the next class.
Oh.
Yep, so it's just homework. Oh, and there you go. Here's the textbook. So you can also pull the textbook up on your iPhones, your iPads, your laptops, wherever you happen to be, and that way you can read it wherever you are. So that's the text. See, it loads pretty quickly. I mean, what does it take? 3 seconds to load this page. All right, any other questions? Well, I tell you what, you might have a question right now, or you might not even know you have a question right now, but you do have a question. And so whenever that question occurs to you, please email me or just come by my office, and I'll sit down and I'll start doing my math lab with you. Like I'll just walk you through the steps to make sure you're all set up, okay? All right, great. Well, that's my math lab, and now we're ready to keep going. So we're gonna go ahead and dive in and keep working, folks. I think we left off last time on question number 7 or 8. Is that correct? Did we leave off on question 7 or 8? Which one did we do? Oh, I had you circle 8. We did 9. And then I had you circle 10. Okay, so we're actually done with those. And what was the main takeaway that we learned about subtracting parentheses? When you subtract a parenthesis, what do you have to do? Yeah, change all the signs inside. That's the shortcut, right? You can always say, okay, that's a -1, so then distribute the -1 and multiply all those numbers times -1. But you can also just remember the shortcut that when you subtract a parenthesis, you're changing all the signs inside. Okay. So, moving on. Let me just look a little better. There we go. Hey, by the way, does the board look better? I fixed it all by myself. See, when I came in here and that board was all crazy and askew, that was my word problem. I was like, oh man, how do I fix this? How on earth am I going to do it? I didn't want to do it. I wanted to go to sleep and have a snack. But I pushed through, folks, and I figured out how to fix it. Just like all of you will push through with word problems and find success. So here we go, folks. Find the perimeter of the geometric figure. Well, first of all, what's the etymology of perimeter? Yeah, a round measure. Peri means around, meter means measure, so to measure around. So what are we going to do to find the perimeter? You just add them all together, right? So you add them all together and you combine like terms. I don't think we need to do that particular problem together, but I will just ask you, do you have to slap parentheses around each of those? In order to add them together, do you have to first put them in parentheses? No, you don't have to. You can just start adding them together. I've seen people solve this from simply writing them all down in order. So maybe I would write down, if this was me, I would say r cubed plus r squared plus 3 plus 5r squared plus 3r plus 6r plus 5. That's probably what I would do. And then I would go back and say, okay, there's all my r cubed, so it's r cubed. And then here's my r squared, so that's 6r squared. And then there's my 3r, my r's, so that's 9r. And then there's my 3 and my 5, so that's 8. Did anyone else get that in? Okay. But I know other people who they might look at that, and maybe they would just stack all the terms on top of each other as they wrote them down. And that would be very clever. So I could say, okay, there's one r cubed term, and then I have a 5r squared, and I also have an r squared. And then I have a 3r, and I also have a 6r, and I also have a 3, and I also have a 5. So you see what I did there? As I took the information, I wrote them down in order of decreasing powers, and I stacked the like terms on top of each other so that now I can add them all together and say 1r cubed plus, that's a 1, 6r squared plus 9r plus 8. Does anyone like that method? It's perfectly fine if you want to do it that way. If you want to write them down linearly in order, you can do that too. What you have to do is something. All right? Don't do nothing. If you just wrote down the answer, I probably wouldn't give you full credit for that, because that would appear magical to your audience. You know, how did your audience know what you just did? If you just write down the answer, that's not really enough. You'd want to show some sort of methodology for what you did so that your audience could follow along and say, oh, okay, that's what you were doing. All right. That's it for section 5.1. That was just combining like terms, perimeter, and that's it. So when you go home tonight, you can definitely do all of 5.1 on your math lab homework. So let's keep going. 5.2. It says write the expression using exponents. Well, first of all, what is exponent? What does that word mean, exponent? What is an exponent? What is an exponent? What's an example of an exponent? X squared, what'd you say? Someone else said something? No? I lied. Okay, yeah, x squared, right? That's an exponent. Typically when we look at exponents such as x squared or x cubed, what part of that is the exponent? Yeah, the little teeny number, right? That little teeny number right there is technically called a superscript. That's a superscript. It's a tiny number and it's written up high. But what does it mean? You know, what does x squared mean? Jackie, what does x squared mean? Yeah, you multiply it times itself twice, right? What does x cubed mean? Tim? Yeah, you multiply it times itself 3 times. So fundamentally, folks, an exponent means repeated multiplication. That's it, repeated multiplication. It tells you how many times to multiply something times itself. So if somebody walked up to you on the street and they were like, hey, what does exponent mean? You said, oh, you mean repeated multiplication? And they say, oh, yeah, that's right. Okay, so how would you rewrite x times x times x times x times x with an exponent? Deegan? Yeah, x to the 5th. And how would I write down b plus c times b plus c times b plus c? Sydney? Yeah, b plus c to the 3rd. Do I need the parentheses, folks? Definitely need the parentheses, right? Wouldn't it be confusing if you wrote down b plus c cubed? What does that look like? It looks like only c is being cubed and not the b. So you definitely need the parentheses to be clear. Okay, how would you rewrite this with an exponent? 1 over 5 times 5 times 5 times 5. Other Jasmine. Wait, is other Jasmine? Yeah, there you are. Jasmine with an S. How would I write this one? Yeah, 1 over 5 to the 4th. What about this one? Negative 7 times itself 4 times. How would you write that down, Chris?
Parentheses negative 7x, parentheses power 4.
Yeah, power of 4, sorry. Absolutely. Do the parentheses, do they matter?
Yeah.
You need the parentheses, yeah. Because it'd be very different if you wrote negative 7x to the 4th. Because in that case, only the x is being raised to the 4th power. Whereas what you really need is the whole thing being multiplied to the 4th power. And then how about this last one? Half, 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 half. How would you write that one down, sir?
1/2 of C6.
Yeah, 1/2 in parentheses to the 6th. Okay, so that's the basic idea that exponents simply mean repeated multiplication. Can an exponent only be a whole positive number? Like, does it mean anything to make an exponent anything other than a whole positive number? For instance, what's 5 to the power of 0? Yeah, so some of you are starting out 1, and that's the correct answer. But a big question would be, well, why? Why is 5 to the power of 0 equal to 1? After all, if an exponent means repeated multiplication, how do you multiply 5 times itself nonce? Or no times? You know, how do you even do that? You're like 5 times, but then you do nothing. Here's another question. What's 5 to the power of -1? You might know the answer, but again, does that even make sense? How do you multiply 5 times itself -1 times? Here's another question. What about 5 to the 1/2? Can you multiply 5 times itself only half the time? What would that even look like? So, and then maybe even another fraction like 5 to the 2/3. What would that even mean to multiply 5 times itself 2/3 of the time? So these are interesting questions that mathematicians wanted these things to mean stuff. Like we wanted these expressions to actually mean something just as obvious and intuitive as a normal positive whole number, such as 3 or 4 or 5. So you may or may not already know the answers to these questions, but we're going to go ahead and review these definitions and even suggest where they came from. So what I'd like you all to do is switch over to your other packet, and I'm calling this an interlude. Who knows what an interlude is?
Like an intermission, right?
Yeah, it's like an intermission. It's like you stop the main movie, and in intermission, you kind of take a break, you get a snack, you go to the bathroom, then you come back and you finish the movie. An interlude is just kind of a brief pause while you do something else, and then you go back to your main work. So we're not doing the notes packet right now, we're doing this interlude. I'm not going to collect this, but I do expect you to still write everything down because these are valuable notes for you to keep for yourself. So, an interlude. An exponent simply means what? Repeated multiplication. And so 2 to the 5th is actually equal to 2 times 2 times 2 times 2 times 2 times 2. And x to the 4th is really equal to right, it's just repeated multiplication. So the first thing that I'd like to share with you is in this class, it is very helpful and valuable to be familiar with powers of numbers. So for instance, I gave you these 4 columns of powers of numbers because I'd like you to somewhat memorize these numbers, or at least be familiar with them. So for instance, let's do the 2's first. Let's calculate out some powers of 2. Try to do it in your head without the calculator. 2 to the power of 1 would be 2, right? So what's 2 squared? 2 times 2? 4. Everyone try to say it as a group. This will be fun. 2 cubed, so 4 times 2 is 8. And then 2 to the 4th, so 8 times 2 is 16. And then 2 to the 5th, so 16 times 2 is 32. And then 32 times 2 again? 64. And then 64 times 2 again? 128. And 128 times 2 again? This was trickier, right? Yeah, 256. And then 256 times 2?
512.
Now 512, you know that because 250 times 2 is 500 and 6 times 2 is 12, so 512. And then finally 512 times 2? 1024, okay. At least that many powers of 2, I'd like you all to start working on memorizing. So maybe the next time you're standing in line somewhere, you can just start counting on your fingers like, okay, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. So just start practicing it. Because if you're just walking down the street and you saw the number 256 somewhere, like on a road sign, I want you to be like, hey, that's a power of 2. Right? Just to start recognizing it. Just to be, oh, yeah, that's a power of 2. You might not remember which power of 2 it is, but you would recognize it as a power of 2. Right? So that's important. Now, the 3's, you don't have to memorize as many 3's. Textbooks don't go very high with 3's. Textbooks go very high with 2's. They'll use numbers like this. But with 3's, they don't go very far. They start with 3, 9, 27, 81, and then peter out. You might see a 243. And again, you just want to be familiar with it. Familiar enough that if you were doing a math problem and you see the number 243, you would say, aha, that's a power of 3. I bet that matters. Right? Because the textbook wouldn't have chosen 243 instead of 245 unless they meant to. So you want to work on memorizing those. How about your powers of 5? What are the powers of 5? Should we try again? 5 times itself, once is 5, and then times 5 again? 25. And times 5 again?
125.
125, because 5 quarters is $1.25. And what about times 5 again? This is tricky, but you can all do it. I believe in you. What's $1.25 5 times? If you have $1.25 5 times, how much money would you have?
525.
More than 525. You'd have 6.25. Right? If you had 5 of these, that'd be $5, and then 5 quarters, which is $1.25, so that'd be $6.25. So it's easy to think about quarters when you do this kind of stuff. Okay, that's it. That's as far as you need to go with 5s. Again, if you saw 6.25 somewhere on a piece of paper, you'd say, hey, that's the power of 5. You might not remember which power of 5, but it's important that you recognize it as power of 5. Now, how about the powers of 10? You should be able to do all of these. So 10 to the first is 10, and then 10 times 10 is 100, and then 10 cubed is 1,000. What's the general rule for a power of 10? You add a 0, and how many zeros will there be? The same as the exponent. Yeah, exactly right. So 10 to the 5th, there should be 5 zeros. And 10 to the 7th, there should be 7 zeros. Right, so in general, we all know how to change a power of 10 into the number, or to take the number and turn it back into a power of 10. Again, these are all just numbers that I want you to become friends with, so that you would recognize them on sight. Again, you might not know that 243 is 3 to the power of 5th, but at least you would know that it's 3 to the power of something if you saw it on the street. Okay, let's keep going to the page. Now here's my big question for you. We're going to understand where these other exponents come from and why they mean what they do, right? Because whole number exponents make sense. It's just repeated multiplication. But what if the exponent is not a positive whole number? What if it's 0 or a negative or a fraction? You know, how do we know what these things? First of all, if I give you this problem right now to do, how would you do it?
I would multiply 5 by 2.5.
Unfortunately, that wouldn't work. But that was a nice idea. I liked your idea. If you did 5 times 2.5, that would be 5 times itself. I see what he was going for there. You all see what he was trying for there? He was multiplying it times half of itself. Unfortunately, that's not what a repeated multiplication really means. But I'm glad you suggested it, Matthew, because this is what our intuition might think. You know, multiply it times half of itself. But in fact, that wouldn't give us the answer. So how would you solve this if I said, hey, quick, solve it? You would type it into your calculator, right? You can just type it into your calculator. You all have a calculator. Your calculator has an exponent button. So just for fun, well, we'll do it in a second. Let's go ahead and start here. Question number 1, what happens when an exponent is 0? Question number 2, what happens when an exponent is negative? So folks, here's what we're going to do. Can we answer this question yet down here? We can't answer those just yet because they're negative. Can we answer these questions up here? Yeah, because they're positive. Let's go ahead and fill in all the positives. So 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 16, 32. Oops, 32. We're just going to study those numbers and see if we can figure out what numbers we should put in down here. So let's go all the way to the top of the list. From the top of the list, what's happening on the right-hand side? Every time we move down a bump, what did we just do? How do you go from 32 to 16? You divide by 2, right? And then what about to go down from 16 to 8? What do you do? You divide by 2 again, right? And then to go from 8 to 4? You divide by 2 to go from 4 to 2? You divide by 2. Is that fair? That we're simply doing that over and over. And that makes sense because what's an exponent? Repeated multiplication. So if we're going downward, it's repeated division. Okay, now that's the right-hand side. What's happening on the left-hand side? 4, 2 to the 3, 2 to the 2. What happens as you go down 1? Yeah, you subtract 1 from the exponent, right? So on the left-hand side, we're simply subtracting 1. All right, well, it is at this moment that mathematicians simply agreed we want the pattern to continue. We want mathematics to be consistent. We want a pattern to start at one end to go ahead and continue on. And so we assume that it just continues. So what would my next answer be? What's 2 to the power of 0? It would be 2 divided by 2, which is 1, because that's just the pattern continuing itself. Likewise, on the left-hand side, we subtracted 1 from the exponent, and we got 2 to the power of 0 is equal to 1. Well, let's continue the pattern. What happens if I go down another time? What would the next number be? 1 divided by 2, which, if you type it in your calculator, what would you get? 1 divided by 2. You get 0.5. Let's not write down the decimal. Instead, just write down the fraction, 1 divided by 2. And that's what your answer would be. If you take 1 and divide it by 2, it's just 1/2. Now you'll notice that's still 0.5. That's still the same answer you get on your calculator. What happens if we go down again? What's 1/2 divided by 2? It is 1/4. And everyone convince yourself, if you do 1/2 divided by 2, well, in order to divide a fraction by another fraction, they both have to be fractions. So that's 1/2 divided by 2, 2/1. And how do you divide by a fraction? Instead of dividing by a fraction, you
Invert and multiply.
yeah, invert and multiply. You multiply by the reciprocal, right? So this is really 1/2 times 1/2, which is 1/4. So yes, indeed, it really is 1/4. So what would happen if we went again? What's 1/4 divided by 2? This would be 1/8. You could do the calculation the same way. And at this point, what do you notice about the fraction 1/2, 1/4, 1/8? It's just the exact same numbers up top, except now all those numbers are in the denominator, right? So what's 2 to the power of -4? 1/16. And what's 2 to the power of -5? 1/32. So that's the definition for a 0 exponent, and that's the definition for a negative exponent. So let's answer the question. What happens when the exponent is equal to 0? What's anything to the power of 0? 1. So you can go ahead and write down anything to the power of 0 is equal to 1. Anything to the power of 0. Oddly enough, except for 0. If you want to make a note to yourself, you can say that 0 to the power of 0 is actually undefined, but we'll never use that. And you can type that into your calculator, 0 to the power of 0 is undefined, you get an error message. But anything else, you can raise it to the power of 0 and the answer will be 1. Okay, question number 2. What happens when an exponent is negative? So what happens when the exponent is negative? It becomes a fraction. That's a good way of saying it. What else could we say? It becomes a fraction. What technically happens here? Yeah, it's 1 over the number. So, for instance, 5 squared would be 25, whereas 5 to the -2 would be 1 over 25. And what do you call that when you... We're not just turning something into a fraction, we're doing the reciprocal. Yeah, we're taking the reciprocal of the number. That's what a negative exponent means. What happens when the exponent is negative? You take the reciprocal. So you have x to the power of -n would actually be 1 over x to the power of n. So you take the reciprocal and the negative power becomes positive. So for instance, if you had 5 to the power of 5 to the power of -3, that's actually 1 over 5 to the positive 3. Okay, so a negative exponent, you take the reciprocal, and what happens is the number that was in the numerator gets pushed into the denominator, but the negative exponent becomes a positive exponent. And that's what it means for a exponent to be negative. You'll notice now if you go down here and look at these numbers, what I could have done was just wrote 2 to the -2 becomes 1 over 2 squared. And 2 to the -3 becomes 1 over 2 cubed. And 2 to the -4 becomes 1 over 2 to the positive 4. And 2 to the -5 becomes 1 over 2 to the positive 5. So what's the main word that you should think of when you see a negative exponent? Reciprocal. Yeah, negative exponent means reciprocal. Okay, well folks, that's where a 0 exponent came from, and that's where a negative exponent came from. I wanted to show you kind of where that came from to let you know that this is a kind of an intuitive idea about where negative and 0 exponents come from. The next couple, fractions namely, I don't have necessarily a quick proof for you to put on the board, but if you want to think about it and then come ask me about it, I would show you after class. So, turn the page. What happens when the exponent is a unit fraction, such as 1/2? All right. So what happens when an exponent is a fraction, such as 1/2? What does that mean? Does anyone remember from previous math class? By definition, so you might just want to write, by definition, x to the 1/2 is the same as the square root of x. A fractional exponent, provided that fraction has a numerator of 1, is simply the root. So x to the 1/2 is equal to the square root of x. What would x to the 1/3 be? The cube root of x. Yeah, the cube root of x. And so on. X to the 1/4 would be the 4th root of x. X to the 1/5 would be the 5th root of x. That's the definition. So when we see, like for instance, 4 to the 1/2, don't tell me the answer, but tell me how to rewrite it. How would I rewrite 4 to the 1/2? The square root of 4. Right? How would I rewrite 9 to the 1/2? The square root of 9. And how would you rewrite x to the 1/2? The square root of x. And then, of course, you'd answer. The square root of 4 is what? 2. And the square root of 9 is 3. So we call those unit fractions. Okay, a unit fraction, such as 1/2, is a unit fraction because the numerator is 1. So unit refers to the number 1, and a unit fraction is any fraction whose numerator is 1. The denominator is automatically the type of root that it is. All right, well, that's the definition there. Question number 4, what happens when an exponent is any other unit fraction? I guess I already said that. So 8 to the 1/3 is really what? The 3rd root of 8. Well, what's the 3rd root? What does that mean? What does that mean to take a cube root? I'll motivate you with this. What would 2 to the power of 3 be? 2 cubed means what?
2 times 2 times
2 times 2 times 2, 2, which is 8. So what would the cubed root of 8 be? The answer would be 2. The cube root of 8 means what number can you multiply times itself 3 times to get 8? And what number can you multiply times itself 3 times to get 8? 2. So the cube root of 8 is 2. Likewise, what would the 4th root of 16 be? So 16 to the 1/4 is really the 4th root of 16. Now what would that mean? What number can you multiply times itself 4 times to get 16? The answer is, again, 2, because 2 times 2 times 2 times 2 is 16. All right, and this one is in the same vein. 32 to the 1/5, how would I rewrite that? The 5th root of 32. And what number times itself 5 times would equal 32? 2. So all of those, the answer were 2. I was just demonstrating what a cube root and a 4th root and 5th root is. Aha! But since you've all started memorizing your powers of 3, who would like to try this one? What's the cubed root of 27? What number times itself 3 times would equal 27? 3. Yeah, 3, right? That was from our list. What about the 5th root of 243? What number times itself 5 times would equal 243? That's also 3. Go back and look at the first page. What was 3 to the power of 5? 3 to the power was 243. Yeah, 3 to the power of 5 was 243. Yeah. So this is one reason why it's really important that you memorize or at least are a little familiar with powers of numbers, because math textbooks will frequently give you things like the 4th root of 16 where they expect you to be familiar with the fact that 16 is the power of 2. And that's how you solve that problem. Okay, so what happens when an exponent is any other unit fraction? Well, any x to the power of 1 over n is the nth root of x. That's the definition. The definition. As a bonus question, what's the 13th root of 1? You know, 1, right? What number times itself 13 times would equal 1? 1. 1 times 1 times 1 times 1. What's the 4,000th root of 0?
Is it 0?
0. What number times itself 4,000 times would equal 0? 0. Because 0 times 0 times 0 times 0 times 0. Yeah. Okay, so that's all the different types of roots. Next question. What happens when an exponent is a regular fraction? Okay, a regular fraction, like a number over another number, not a unit fraction, because we now know that all unit fractions represent what? Roots, right? All unit fractions represent roots. Well, what if you have a numerator? What if the numerator is something other than 1? It's just a regular old fraction. What do we do then? And you can see we have these example problems here. 8 to the power of 2/3, 16 to the power of 3/4, 32 to the 2/5. What do you do then? Yeah, the denominator is the root. Very good. Yeah, and the numerator is the power. I hope that seems natural and intuitive. Let's write it down once. What if you had x to the power of the fraction, and just for fun, let's all write down the fraction 2/3. So x to the power of 2/3. Just like Jackie just said, the denominator is still the root. Denominator is the root, just like we have been saying. So whatever the denominator is, that's the type of root that you're taking. Whereas the numerator is the regular exponent. Oh, I'm going to write that out. Numerator is the exponent. And by exponent, I mean the normal exponent, repeated multiplication. See, this numerator is just a 2, so that would be squared. So how do we rewrite x to the 2/3? Here's how I want you to rewrite x to the 2/3. First, you do the denominator. It might feel a little weird to start with the denominator first, but first, you would do the denominator. So we're taking the cube root of x, right? And then you slap it inside some parentheses, you do the numerator as the power. That's how you break that into 2 different pieces of information. So a fraction is really 2 different pieces of information. First, you either do the denominator, which is the root, and then you do the numerator, which is the exponent. That's the order of operations. So let's try it. How would I rewrite 8 to the power of 2/3? What do you do first? What do you do first? Kind of calling everybody on this one's Amber. Thanks for volunteering. What do you do first?
The cube root.
Yeah, the cube root. So first I'm going to do the cube root of 8. And then what do you do second, Amber?
Square.
You square it. Okay, very good. So you do the denominator first, then you square it. And everyone, what is the cube root of 8? What number times itself 3 times equals 8? 2. So now we have 2 squared. And what's 2 squared? 4. And believe it or not, if you type 8 to the 2/3 into your calculator, the answer will be 4. All right, how about 16 to the 3/4? So again, you do the denominator first, and then you do the numerator. So let's see here. How about Ariana? Ariana, what do I do first for 16 to the 3/4? Yeah, you 4th root the 16, and then you cube it. Notice I'm putting parentheses. I hope you're putting parentheses too. You got to cube root the number, and then parenthesis, then cube it. So what is the 4th root of 16? Anyone ever? 2, because 2 times 2 times 2 times 2 is 16. So that gives me 2 cubed, and then 2 cubed, 2, 4, 8 is 8. And so 16 to the power of 3/4 is equal to 8. And one more example. Daniel, what would I do first for 32 to the 2/5? Yeah, you 5th root the 32, and then? Sorry? Yeah, the power of 2. And the 5th root of 32 is 2, and 2 squared is 4, and that's your answer. The answer is 4. Folks, everybody in the room has a calculator, so I would like you to go ahead and type, everybody, let's do 8 to the 2/3 in your calculator. In your calculator, you folks might not know where this button is. It's the caret button. It looks like that. That's your exponent button. For some of you, that's your exponent button. Very important. If you're going to do 8 to the 2/3, you'd have to write 8 caret parenthesis 2 divided by 3 parenthesis. If you want to do this in your calculator, and I'm thinking a lot of you have scientific calculators, it has to be 8 caret parenthesis 2 divided by 3. And the answer that all of you should get is 4. Now, not all of your calculators has this caret button. Maybe you have a calculator that has a button that looks like x to the power of y. Okay, if that's you, if you have a button that says x to the power of y, you would have to type 8, this button, x to the power of y, parenthesis 2 divided by 3 parenthesis. So everyone on your own calculator, calculate 8 to the power of 2/3 and see if you got the answer of 4. And I'll just walk around real quick, and if anybody has a calculator. Yeah. 8 to the power of 2 divided by 3. Great. And if you have any questions, now some of you don't have your calculators today. Make sure you start bringing your calculators. Make sure you start bringing your calculator, because we'll be doing these things in class, and I want you all to be able to do it. Oh, sorry. All good. Great. Great. I think you do have the, oh, it's y to the power of x. Same thing. I'm so sorry. So you do 8, and then y to the power of x, and then parenthesis 2 divided by 3, parenthesis equals. Come on. Yeah, it worked. Did it work out for you? Up to Good work. Good work. Did it work out for you? Yes, yes. Oh, good. Hey, very nice. Thank you for helping out.
Hasn't it?
Hey, Chris, did it work? Oh, it didn't?
Here. So you have the X to the something button. So you type 8. What you got to do? Oh, whoa. I don't know what that is. 8. And then that. And now parenthesis 2 divided by 3. There you go. And then, yeah, perfect. You got it.
Okay, it worked. It worked. Deacon, did it work? Bring it next time. All right, folks. Thank you very much. We're not going to do question number 6 because that gets into logarithms, which we're not doing in this class. If you're curious about the question, you can always come ask me about it after class. Let's go. The next page of your interlude is about exponent rules. So far, all I've done with you is talk about different types of exponents that are not positive whole numbers. So we now have a lot of different types of exponents that we can compute, from a positive whole number to 0 to a negative whole number to a unit fraction to a regular fraction. These are all the different types of exponents you can do now in your head as well as on your calculator. These are exponent rules, meaning combining more than one expression together. Like, what if I wanted to multiply, as an example here, what if I wanted to multiply 5 cubed times 5 to the 4th? Okay, so now we're talking about combining multiple exponential expressions together and computing those. Okay, so our very first one, the product rule, you see it's already written up there for you. It says a to the power of x times a to the power of y is equal to a to the power of x plus 1. Maybe you've seen this rule before. Let's go ahead and apply it. What would 5 cubed times 5 squared equal? 5 to the power of 3 plus 2, which is 5 to the power of 5. Now, 5 to the power of 5, we're capable of doing that one. 525, 125, 625, 3,125. That's pretty big to do in your head. I don't expect any of us to do that in our head. So you could type that into the calculator and you get the answer, 3,125. What about the next one? 9 squared times 9 to the 6th. Let's see here. If I count on everybody, let's say Jesse. Yeah, 9 to the 8th, because it would be 9 to the power of 2 plus 6, which is 8. Now, 9 to the 8th is way too big. Nobody's going to do that in their head, not even me. You could type it into your calculator, but you get a really nasty answer. It'd be like in the millions or the billions. So you can just leave it like that. The answer is just 9 to the power of 8. You don't have to compute it. Okay, what about 3 to the negative 4th times 3 to the negative 3? What would that be? Let's see here. Don?
3 to the negative 7.
Yeah, 3 to the negative 7. You just add 4 plus, well, negative 4 plus negative 3 is negative 7. Can I leave it like this, or should I do one more thing? Yeah, we're going to put it 1 over 3 to the 7th. Because remember, what does a negative exponent mean? Reciprocal. So you would want to go ahead and do it, because we want to leave all of our answers with positive exponents. Okay, and then what about 10 to the 5th times 10 to the negative 5th? That's a curious one. Eduardo? Yeah, 10 to the power of 0, which is 1. Now, that's a fun one, because this gives us another proof about why 10 to the power of 0 is equal to 1. Because 10 to the 5th times 10 to the negative 5th is 1 over 10 to the 5th. And what happens if you have a 10 to the 5th on top and a 10 to the 5th on bottom? Cancel out. They cancel out and you get 1. So that's another reason why anything to the power of 0 is equal to 1. Okay, very nice. That's the product rule. It means when you multiply expressions, you add the exponents. So what happens when you divide expressions? You subtract the exponents. So that should be a natural consequence. So you go ahead and try it out. 4 to the 7th divided by 4 squared would be 4 to the 7 minus 2, which is 4 to the 5. Now again, even though we could all probably do 4, 16, 64, 256, 1,024, you don't need to do that off the top of your head. You wouldn't even have to type it in your calculator. Just leave it as 4 to the 5th. So what would 8 to the 9th divided by 8 to the 4 be? That's 7. Yeah, 8 to the 5th. Exactly right, because 9 minus 4 is 5, so 8 to the 5th. And what would 7 to the 3rd divided by 7 to the 5th be, Sarah?
7 to the negative 2.
Yeah, very good. One thing at a time. So 3 minus 5 is negative 2, so it is 7 to the negative 2. But then, correct, Sarah, you take the reciprocal and write it as 1 over 7 squared. Now, 7 squared. Should we leave that as 7 squared, or should we compute that? Probably compute it. I mean, 1/49th is a very reasonable answer. Right? So there's no general rule for this. If it's small enough that you can compute it and it's a small number, you should compute it. But if it's going to be something over a couple hundred or a couple thousand, just leave it in exponential form. Okay, same thing goes 10 to the 6th divided by 10 to the 6th. Dawn?
0.
Yeah, 10 to the 0, which is another natural explanation of why anything to the power of 0 is equal to 1. Okay, so product rule means you add the exponents. Quotient rule means you subtract the exponents. Here's our next rule called the power rule. The power rule, you raise an exponent to an exponent. And what happens when you raise an exponent to an exponent? You multiply the exponents. Yeah, that's the rule. So if you want to write multiply the exponents. So in this case, 2 cubed squared. So the exponents are a 2 and a 3, so you multiply them. And what would you get, Vanessa? What did you say? Yeah, 2 to the 6th. Perfect. So 2 to the 6th. You even multiply even if one of the exponents is negative. So what would 7 to the negative 3 to the power of 2 be, Jasmine, with an S? Which becomes? Because it's a negative, you would go ahead and, yeah, 1 over 7 to the 6th. Great. And then 48 to the negative 5th, Leslie? This Leslie up front? Yeah, 4 to the negative 40, which would really become what? Because it's a negative. Yeah, 1 over 4 to the 40. Great. And then this last one is fairly clever. What's 10 cubed to the 1/3? What's 3 times a third, Matthew?
I'm not sure.
Well, that's okay. You can be not sure. What's 3 times 1/3? Yeah, you put the 3 over a 1, and then you multiply straight across, and you get 3 over 3, which is what, Matthew? 1. Yeah, 1. So then this is 10 to the 1, which is 10. Okay, so these are all of your exponent rules so far. You've got your product rule, addition, quotient rule, subtraction, power rule, multiplication, and then we just have a couple more applications of that. So what about the power rule when you have more than one thing inside of a parenthesis being raised to a power? What do? What does the formula imply you do? You kind of distribute the outside exponent and multiply it times the inside exponents. The word distribute is not technically accurate, but that's how I always think about it in my head. I always think, oh, I'm going to distribute the exponent to both of those exponents, and then that way I have a to the xz and b to the yz. I don't know what the right word is for that, but you do still multiply the outside exponent times all the inside exponents. Maybe that's the best way to say it. You multiply the outside exponent times all the inside exponents. So, as our first example, 5 cubed, 7 squared, all to the 6th. Genesis? Yeah, exactly right. That's it. Go ahead and write down the next couple, folks. You can do those next couple to practice. All right, that's our break song. Let's just finish this and then we'll take a break. So just to call out a few people. Kim, what did you get for 3 squared 8 to the 7th to the 4th? Yeah, very good. 3 to the 8th, 8 to the 28th. And actually, I'm not going to finish the last because I think we're all on the same page. Fraction rule. Everyone, I'm sorry, my parentheses did not show up. That should be the fraction a over b in parentheses to the power of x. So what happens when you raise a fraction to an exponent? How would you verbalize this to someone? What happens when you raise a whole fraction to an exponent? You raise both the numerator and the denominator to that exponent. Yeah, we don't really multiply anything, but I knew what you were saying. When you raise a fraction to an exponent, you raise the numerator and denominator to that exponent separately. So for instance, 5/3 cubed would really be 5 to the 3rd over 3 to the 3rd. So you take the outside exponent 3 and you apply it to both the numerator and the denominator. These numbers are small enough that you could do in your head. What's 5 cubed? 125. And what's 3 cubed? 27. Yeah, those you can totally do off the top of your head. Likewise, 7/4 squared. You can probably do that one in your head too, because that'll be 7 squared over 4 squared, which is, yeah, 49 over 60. All right. Well, folks, these are our exponent rules. I highly recommend that you memorize them to the point that you could recognize them on sight. That you wouldn't necessarily have to go check your notes and be like, oh yeah, how do I do that one again? You'd want to be able to do all the problems like these just by looking at them. All right, so let's see. That's it for our interlude, which is perfect timing for our break. So the time is 1:42, so everyone will be back in the room at 1:51. So we can start. Manuel, you want to go try to drop that thing off? You've got 10 minutes. I bet you can do it. All right. Can you tell me one more time? Kaizenine. But how do you use that? Oh, Kaizenine. Like Kaizenine or Kaizen? But is it a ka or a ka? Oh, it is a ka. Wait, let me say. My daughter's name is Eloisa, not Eloisa. A lot of people say Eloisa. No. Eloisa. So you're Kaizenine. Say it again. Kazinia. Okay, it's on the second one. Okay. Kazinia. I can say that.
I think of cousin and then me.
Ah, yeah, there you go. Kazinia.
Okay, I like it. Yeah, because anyway, so it takes me a while to
It's
get there.
okay.
Like Jack. No, I got it. Jack. All right. Then I get that. Zinnia. There we go.
After almost semester.
And then well, sometimes I have.
They don't touch hands with
Well, thank you. I appreciate your kindness. Yeah. Oh, yeah, that's fine. It's got that nice little acid.
Oh, wow,
Yeah.
Yeah, what is it? Oh, yeah, sure. In fact, I'll start a little pilot. If you want. And then identify everybody. Use yours as the example. Yeah, that's perfect.
Everything's always secure. I'd like to hear. I like.
All right, folks, I think everybody is back. I think we need math. All right, let's get started. So, what we just did was an interlude. The interlude was just my own way of presenting the material to you so that you could then tackle these problems. So I'm actually going to give you many of these exponent problems as practice because I think you can now do it. So for instance, number 17. What's negative 9 to the 5th times negative 9 squared? Yeah, negative 9 to the 7th, because we just add the exponents, right? Likewise, what about 18? We haven't done a product of 3, but what do you think the answer would be? Yeah, m to the 16th, because you just add them all together. And that one up there would be negative 9 to the 7th, because you just add the exponents. So I'm not necessarily going to do all these problems with you, because I want you to now practice them. I did the notes with you. But let's just take a look at a couple of them. For instance, number 20 is a little tricky. How do we interpret number 20? On the one hand, what is that exponent telling us to do? Yeah, multiply 3t times itself. How many times? So we would have 3t times 3t times 3t times 3t. Well, that's a lot of writing down 3t, right? But what's the rule? Well, we talked about a rule where if you had multiple things inside of a parenthesis, all raised to an exponent, the key is in noticing that the exponent on the 3 is a 1. That's really 3 to the 1st. And the exponent on t is really t to the 1st. So how do we quickly get our answer? We multiply the outside exponent times all the inside exponents. So what would the solution be?
7t7.
Yeah, 3 to the 7th, t to the 7th. That might not be immediately obvious, but again, if you did take the time to write down 3t times 3t times 3t times 3t times 3t times 3t, 1, 2, 3, 4, 5, 6, 7. How many 3's are being multiplied together?
7.
7. And how many t's are being multiplied together?
7.
7. So the answer once again becomes very reasonable. It's a very reasonable answer. It makes sense. Okay, now how about this one? Negative 2 to the 4th squared. What makes this problem tricky?
Sign.
Yeah, a negative sign, right? So how do we interpret the negative sign? If we wanted to, we could just do it by definition and say this is negative 2 to the 4th times negative 2 to the 4th, right? Because negative 2 to the 4th squared means multiply times itself twice. And we could also, furthermore, do the 2 to the 4th. That's 2, 4, 8, 16. So that's negative 16 times negative 16. And a negative times a negative is positive, and 16 times 16 is 256. So you can always baby step your way to the answer. Right? You can baby step your way to the answer by just thinking about what all these definitions mean. But this begs the question, why is negative 2 to the 4th negative 16? Did anyone disagree with me on that one? What's the difference between, actually I'll do it over here where you would write it as well. What's the difference between negative 2 to the 4th and negative 2 to the 4th? Is there a difference between these two expressions?
Yep.
There is a difference. If you type them into your calculator, you'll get a different answer. That's the key. If you type this in your calculator, if you type that into the calculator parentheses, you'll get a different answer. What answer will you get here? Negative 2 times negative 2 times negative 2 times negative 2. That would be 16, positive, because a negative times a negative is positive, and another negative times a negative is positive. Whereas here, if you type this into your calculator, what will you get? Negative 16. Because technically, there's a negative sign floating in front of 2 to the 4th. And in fact, technically, negative 2 to the 4th is negative 1 times 2 to the 4th. Right? So that's very important that you all note that a negative exponential, that's technically a negative 1 being multiplied times that expression. And that's why that's negative 16. So armed with that knowledge, let's do the rule on this one. Technically, there is not just one thing inside this parenthesis. There are two things. It's a negative 1 times a 2 to the 4th, all being raised to the 2. And in fact, to be even more careful, what should I do to my negative 1? I'm going to put it in parentheses. And what is the exponent on the negative 1? Technically. 1. Yeah, there's a 1 there. Now we could apply the rule. Let's see if the rule gives us the same answer. What do I do with my outside exponent? Multiply it times both of the inside exponents. That gives me negative 1 to the 2 and 2 to the 8th. Well, what's negative 1 squared? 1 positive. And then 2 to the 8th, 2, 4, 8, 16, 32, 64, 128, 256. And hey, what do you know? We got the same answer, 256. Now, I didn't want to be confusing by doing this problem twice. I just wanted to show you that there are multiple ways to do the problem. And if you find yourself doing it one way or a different way, that's okay. You can do it in multiple different ways. What's the key? What do you have to show me?
Your work.
You just have to show me your work, right? Because some of you might solve these problems differently. What you can't do is just type it into your calculator and say 256, because then I wouldn't give you any credit. Remember, you're trying to show enough work that an unskilled audience member off the street would be able to walk in and see how you got your answer. So whichever one of these two methods you showed me, I would give you credit for it, so long as you're showing me your work. Okay, moving on. Yes, here we are. We're on number 22. We will do this one together. Now, in number 22, if you just look at the picture, what might you think you're about to calculate? You might think it's perimeter, but what is the problem asking you to do? The area. So you want to be very careful, area versus perimeter. Now, perimeter, we know you add all the sides together. What's the etymology of area? Unfortunately, the etymology for area, I think, is lame. The etymology for area means a level piece of ground. That's almost unhelpful, right? Not like perimetros, measure around something. Area is just a level piece of ground. And that is, if you go back a couple thousand years ago, what was important to people was figuring out how much land they owned. I own this much land, you own that much land, I'm richer than you because I own more land than you do. So they were technically calculating how much land they owned. Because why is land important? What can you do with land? You can build buildings or you can grow crops, and that makes you rich. So if you go back historically, they wanted to know how much area a piece of land was because it was a calculation of wealth. So area means a level piece of ground. And so we want to know how much land is there inside, you know, for growing crops and building buildings. So how do you calculate the area of a rectangle? Area equals, I heard length times width, or what are besides length times width? Base times height. Yeah, base times height. Both of those are perfectly fine. You can do length times width, you can do base times height. Either one of those will work. So in this case, since we're finding area, what are we going to multiply? Yeah, we're going to multiply 4x squared times 7x to the 5th. Notice how different this is from perimeter. Perimeter, we would have been adding all four sides together. With area, we're just multiplying two of the sides together. And so how do you multiply 4x squared times 7x to the 5th? Yeah, you multiply like with like. So you're going to multiply the numbers together. What's 7 times 4? 28. And then you multiply the exponents together, in which case you apply the power or the product rule. So x to the 2 times x to the 5 is really x to the 7. And that would be it. So the area of that figure is 28x to the 7. What's the formula for the area of a triangle? You know, 1/2 base times height. But otherwise, the principle is the same. We have our base, 5s to the 5th. We have our height, 3s squared. And so we would jot down 1/2 times the base, which is 5s to the 5th, times our height, which is 3s squared. And again, you multiply like with like. Now, even right now, you might just want to do on your calculator 1/2 times 5 times 3. Or you can do 0.5 times 5 times 3. Or you can do 5 times 3 is 15 and then divide by 2. What's half of $15? $7.50. So $7.50 and then s to the 5 times s to the 2 would be s to the 7. And that's it. Is that an equation? No, that's just an expression. Right? There's no equal sign. Not yet. So it's just an expression. Is it true or false? It can't be true or false because there's no equal sign. The equal sign is what turns it into a statement, which can either be true or false. Those are just expressions, right? They're not true, they're not false, they're not equations. They're just expressions that you can use to calculate the area of those shapes. Questions about what we just did? Oh, not that? Yeah, which one?
The base.
Yeah, the base times height. Okay, so again, we're going to do 1/2, and then the base, which is 5s to the 5th, and then the height, which is 3s squared. And again, thank you, Crystal, for volunteering to do this problem for everyone. We want to multiply like with like. So what's one set of like numbers up here? Just the numbers. Half times 5 times 3. All on your calculator. What do you get? What's half times 5 times 3? What is 1/2 times 5 times 3? What is it? 250 and 150. 7.5. Yeah. We're not adding anything actually. It's 1/2 times 5, which is $2.50, right? So let's just think dollars. Half of $5 is $2.50. And what if you have 3 250s? How much money would you have? $7.50. Yeah. Oh, okay, yeah. Oh, that's what you meant by add them together. Okay, yeah. So that's 7.5. And then you have s to the 5th times s squared. If you want, you could write that next to each other. S to the 5th times s squared. So what is s to the 5th times s squared? Yeah, using the product rule, which means you add them together. So your final answer is 7.5 s to the 7th. Did that answer your question? Okay. All right, thank you, folks. Thank you, Krista, for asking.
I just missed the first step.
Oh, the first step, multiplying the numbers? Okay, gotcha. Yeah, you can use your calculator, folks. Okay. We're done with section 5.2. Now we're looking at section 5.3. In section 5.3, we are doing what? What would you guess is the main idea in section 5.3? What do you think is the main idea?
Using the distributive property.
Yeah, the distributive property. We'll be distributing. You can tell that from the first couple of problems. We're going to distribute the outside number and multiply it times the inside. And my notes up at the top, I say, remember when distributing. So if you distribute a positive number, what happens? Yeah, like here's a for instance. 3 times 2x minus 7y plus 5z. So what happens if I distribute a positive number? All the signs stay the same, right? You keep the same signs, you just multiply the numbers. So after I distribute, I would have 6x minus 21y plus 15z. All signs stay the same. This is the quick and easy way to think about distribution. If you distribute a positive number, you don't have to be thinking, okay, 3 times 2, that's 6, 3 times -7, that's -21, 3 times 5, that's 50. You don't have to do all that in your head thinking about the positives and the negatives. You just know that when you distribute a positive number, all the signs stay the same. So it went plus minus plus, it still goes plus minus plus. So what about when you distribute a negative number? What happens to all the signs? All the signs change. So all signs change. Now, when we do distribution with a number, that's nice and easy because you're just multiplying like with like and you just multiply all the numbers. So, volunteer to tell us the first solution. How about Amber? Distribute the 9, and what do you get? Yeah? Yeah, very good. Did you all get the same answer? Yeah, that's correct. You just distribute, multiply like with like. But how about this next problem, number 25? Now we're distributing a variable expression. So you multiply the numbers times the numbers, and then you also have to multiply the variables times the variables. So what do we get now? We have to be very careful and slow with this. What's the first one? -12 times, well, if you're distributing a negative, all the signs change, right? So I'm going to go and do that first. These are both minus, minus. So my answer should be plus, plus, right? And then I'll go ahead and do the numbers. 12 times 10, that's 120. And 12 times 7, that's 84. So far I know that's the structure of my answer. Now you may or may not like how I'm doing this, doing the signs, then the numbers, and the variables. And we'll do it a different way as well if you like. But now, what's x to the 7th times x? Yeah, that's really x to the first, right? So 7 plus 1 is 8, so that's x to the 8th. Well, what about the next one? What's x to the 7th times? There is no variable there. Or is there a variable there? Is there a variable right there? Obviously not, right? There's no variable there. And yet, there's a variable there. What is it? X to the 0. There is technically a variable there. It's x to the 0. Because what's x to the power of 0? 1. So how do you multiply x to the 7th times x to the 0? You add the exponents. 7 plus 0 is 7. So it's still just x to the 7th. Okay. I just went through to do that piece by piece to show you that there's at least 3 different parts of your brain that you have to use to do a problem like this. You have to think about the signs, you have to think about the numbers, and then you have to think about the variables. Now you could just do it all at once, right? Instead of doing it piece by piece, you could just look at the first two and say, okay, a negative times a negative is positive 120, and then x to the 7th, x to the 1, that's x to the 8th. Right, so you can do it all together, but just make sure in your head you're thinking signs, numbers, variables, all three things. And then the next one, negative 12x to the 7th times negative 7, that'd be positive 84x to the 7th. However you want to do it, again, that's up to you. Just so long as you're showing all of your work and thinking about all three things, signs, numbers, and variables. All right, let's keep going. Okay, so I have one more problem up there for all of you to try. Go ahead, everybody, and try number 26. Go and try number 26 on your own. If you ever want to check with your neighbor or anything like that while I'm walking around, it looks like most of you are calculating negative 55x to the 14 minus negative 40, well, just minus 44x to the 10. Is that what everyone got? Yeah. All right. Okay, so that's just normal distribution. You distribute once. So how do you do a problem like 27? First of all, you might look at that and what concept might come to mind? When you're multiplying one parenthesis times another parenthesis. What concept is that? What? Yeah, FOIL, right? FOIL is when you would have simply one binomial being multiplied by another binomial, and then you would do FOIL. So FOIL is FOIL, and you do first, outer, inner, last, and that would be FOIL. It's just reminding you to do all the distributions possible. But what's really happening? When you do FOIL, you're really just doing distribution twice, right? You take, let me just delete that. You take the first number, x, and you distribute it to both objects in the second parenthesis. That's the faux. And then you take the second object and distribute it to both objects in the second parenthesis, and that's the ill. So you've got faux, first outer, of distributing the first number to the second parenthesis, and then ill, distributing the second number of the first parenthesis to both numbers of the second parenthesis. That's a mouthful, isn't it? But that's all that's really happening. So how would we go about doing number 27 then? It's not FOIL because you have a trinomial, right? But technically we would do the same thing as what we did here. You would distribute twice. So what's the first thing we'll distribute? The 10p will distribute to all three objects in the second parenthesis. And then what will happen with the negative 1? It will distribute to all three objects in the second parenthesis. Now, nobody would look at that and say, first, middle, outer, inner, middle, last. Fulminal. Nobody would say that, right? That's just silly. It doesn't sound good. And yet, isn't that technically what you'd be doing? First, middle, outer, and then inner, middle, last? Right, but nobody says that. But that's what FOIL came from. FOIL is really just distribution twice, but they wanted to call it something, so they called it FOIL. Well, really, what are you doing? Distribution twice. That's it. So here we're also doing distribution twice. So let's go ahead and try it. Again, you have to be using three different parts of your brain: the sign, the numbers, the variables. So what's 10p times 100p squared? Is it 1,000p cubed? Yes. Yeah? And then what would 10p times 10p? Yeah, 100p squared. And then 10p times 1? Yeah, just 10p. So that was my first distribution. I distributed the first number to all three terms in the second parenthesis. Now I'll distribute the second number from the first parenthesis to all three terms of the second parenthesis. Now when I do that, should I continue writing them linearly out? What should I do instead? Stack them. Yeah, we probably want to stack them so it's easier to combine like terms. So now, -1 times 100p squared is -100p squared. And I stack it right below. And then -1 times 10p, -10p. And then -1 times 1, -1. So now I have everything nice and stacked. I'm going to add all my terms together. I get to cross out the p squared term, cross out the p term, and we end up with 1000p cubed minus 1. Famo Immel. That sounds like something. Famo Immel. All right. So how will you do this problem? The same way. You'll do it the exact same way. If you have multiple colors, you might want to use multiple colors, but no matter what, I would draw these rainbow lines. I call them rainbow lines to remind yourself to do all 6 possible multiplications. Do you guys want to go and try that right now, or should we move on? You go ahead and why don't you all try it right now and compare with the neighbor and see if you ended up with the same thing. I see quite a few of you, the terms are canceling out in this one as well. And once you get them all listed out, a few of them are canceling, which is very convenient. Did you get 125y cubed minus 216? Yep. Oh, good. All right. Now, folks, just as a challenge problem, I was just telling Sydney, but do you think anytime you multiply a binomial times a trinomial, all those terms are going to cancel out? No. So there's probably something special about how these two problems were written. I wonder if you could, off the top of your head, and in fact, I'll go ahead and do one. Let's say I do 3z minus 4. And then there'd be 9z squared, let's see here, plus 12z, plus 16. I claim that that is going to have a bunch of canceled terms, just like the previous two problems. Why do I claim that this, if I multiply it out, is going to end up with lots of canceled terms, and my final answer is going to be 27z cubed minus 64.
Those two last numbers have like terms. 4?
What, these two terms?
No, 12 and 16.
The 12. Oh, these both have, yeah, 16 is divisible by 4, and so is 12. Do you see the pattern? Now, this is just fun. I'm just throwing this out there for fun. Then I'm suggesting to you that whoever the devious textbook author was that made these problems, they were following a pattern that I just followed, and I claim that that will also, the terms will cancel, and you'll get just that simple answer. Do you guys see what I did? Where did I get the 9? Where did the 9 come from? It was 3 squared. Where did I get the 16? The The 4 squared. Where did I get the 12? The 3 times the 4 to equal 12. And provided I keep all the signs the same way, minus and plus plus, and minus plus plus, I think that's the pattern they were using to create these problems. So theoretically now any of you could make up your own problem, which would be essentially just like this. I only mention it because we're going to do a lot of multiplication of binomials, and patterns are going to be very important. Patterns, to just notice those patterns and see how they work. Okay, so let's keep going. Technically, that covers all the information that's on your midway quiz. So I won't give you the midway quiz right now. We'll just keep going. But at the end of class, I'll give you the midway quiz, and you all will give me your student information sheet and the syllabus quiz. And you'll take the midway quiz home, and you can do it tonight, tomorrow, and bring it back on Wednesday. I did put some information up here for you. It says what? The midway quiz is due on the, oh, that might be wrong. Today's the 22nd, isn't it?
Yeah.
Yeah, so it's not the 28th. I'm sorry. It's due next class period. It's due next class period. It's due at the beginning of class, right when you walk in. You can use your book and notes, but you can't use another student or human or Google. And if I see any collaborating on these quizzes, you'll get a 0 and risk further consequences with the math department. So please don't work with another person. Believe it or not, last semester, I still had 2 people who turned in the exact same quiz. Now, what do you think is the probability that 2 students would turn in the same exact work? 50%? 90%? 0%? It's very unlikely. It's very unlikely. So just as a nice little friendly reminder, I know none of you are going to do it, but I find it's important to emphasize that we should all be working independently. Okay, so moving along. Did we already do this? No. Oh, that is the midway quiz. This is a copy of the midway quiz. I'll give it to you at the end of class. Okay, section 5.4. Another interlude. Did you all get this interlude? Or is it just on the next page? Oh, it's part of the same packet. Okay, good. So, interlude. Let's talk about FOIL real quick. We already introduced it. What does FOIL stand for? Yeah, first outer, inner last. Which, again, is just a friendly little mnemonic that they made up a long time ago to help students memorize the process. But what is the process really? Distribute the first number, distribute the second number. Really, that's all FOIL is. So one thing you might have to do is do FOIL with no numbers at all. And that might feel a little weird to distribute without numbers. Well, let's go ahead and try it. What would F be, the F? P times A, so that would be PA. We're just multiplying letters together. And then outer would be P times N, so PN. And then inner, L times A, so it'd be LA. And then last, L times N, which is LN. The important thing is to recognize the pattern. You know, just because you're not multiplying numbers together, the important thing is just to remember what the pattern is of the first, outer, inner, last. Does anyone recognize what we just did? It's a joke. It's a math joke. What did we just do? I foiled the plan. Yeah, okay, well, I thought it was funny. All right, so typically you perform FOIL one step at a time, and then you combine like terms. So the typical way you would do this problem, where I'm about to teach you a shortcut if you don't already know it. The typical way you do it is you do first, outer, inner, last. You say, okay, first, x squared. Then you do outer, 3x. And then you do inner, 5x. And then you do last, 15. This is the classic way of doing FOIL, but it is a little lengthy because now that I've done FOIL, what do I still have to do? I still have to combine like terms, and I get x squared plus 8x plus 15. Okay, well that's how we do FOIL traditionally, but I would like us all to now practice a little shortcut. And the shortcut, you'll notice if you take a look at my next section, I had the x plus 5, x times x plus 3, and then x squared plus 8x plus 15. And that was the answer we just got, right? X squared plus 8x plus 15. Well, how can I rewrite 8? Where did I get 8 from? Yeah, it was 3 plus 5, right? Or 5 plus 3. And where did I get the 15 from? That was 5 times 3. So provided you notice that, then we can start using this as a shortcut. That the middle term of FOIL is always going to be the sum of the two numbers at the end. And so I'm going to write the word sum right here. How did I get the middle term, 8? I just added 5 plus 3. And then what is this one? That's multiplication, which we'll call the product. Product means multiplication. We're going to call this the sum product rule, where if you want to FOIL any two binomials together, and it looks like that, like x plus a number, y, and x plus another number, then the middle term will be the sum of those two numbers, and the last term will be the product of those two numbers. And what I want you to try is to actually say it as you go. You would say sum product. So for instance, I'm going to multiply x plus 6 times x plus 10. You can go ahead and start by always just writing x squared. Right? The first term is always going to be x squared. And now I'm going to say it as I go, the sum. So what's 6 plus 10? 16 is the sum. And now the product, 6 times 10? 60 is the product. So that would be the sum product rule for multiplying two binomials together very quickly. Provided those two binomials are of the form x plus a number times x plus another number. Okay, that's how it's going to work, sum product. So how about the next one? Oh wait, this is not the same. I take it back. So x plus 3 times x plus 8. As fast as we can, it's going to be x squared, and then the sum. What's the sum? 11x, and then the product? 24. So the answer is x squared plus 11x plus 24. Everyone go ahead and write down the answer to the last one. Always start with x squared, and then the sum, and then the product. In this case, you notice the unique fact that 2 plus 2 is 4 and 2 times 2 is 4. But it still worked. Right? So as we continue practicing, we want to keep that in mind. That instead of doing FOIL, we're going to practice sum product. So on the next page, I believe I have a whole bunch of you to try. And I'd like you to just drill it right now. And I'm just going to do a couple with you real quick, because I haven't mentioned the fact that the signs can be plus or minus. So let's try that real quick with plus or minus. I'm going to do the first 3 right here, the first 3 on the left. So everyone start by writing x squared, and then what's the sum? 8 plus negative 3? 5x. And what's the product? 8 times negative 3? Negative 24. So sum product, just like that, you write down the answer without doing FOIL. What about this next one, x minus 8, x plus 3? You write down x squared, and then the sum, what's negative 8 plus 3? Negative 5x. And what's negative 8 times 3? Negative 24. Notice how subtle those two problems are. I just changed the sign on the two numbers, and it did impact the answer a little bit. How about this last one? X minus 8 times x minus 3. You immediately write down x squared. What's negative 8 plus negative 3? Negative 11x. And then negative 8 times negative 3? Positive 24. Okay. Folks, everyone try that. And in your head, again, I really encourage you to try saying sum product. Sum product. To really drill that into your head. That the middle term is the sum, and the last one is the product. And this is a shortcut for FOIL, so that you don't actually have to do first, outer, inner, last, combined line terms. Okay. If you have any questions at all as I'm walking around, I'm making myself available to you. So what would you do right now if you wanted to check your work? For instance, are these equations? They're not equations, there's no equal sign. So they're neither true nor false, you can't check your work. So how do you check to see if, say, I'll do this one right here, x minus 20, x plus 2. I claim the answer is x squared minus 18x minus 40. How do I know if I'm right or wrong?
You have to factor it.
Well, you could factor it, go backwards, and see if it factors back to the original expression. Or you could just do FOIL, right? You could just go ahead and do the FOIL and see if that ends up equaling what you just got. And that's it. Those are your two options. You could either do the FOIL longhand, step by step, and check, or you could factor, which is, of course is just working backwards from there. Okay, questions about this shortcut? It'll be helpful as we proceed through this class that we're using this shortcut whenever possible, as opposed to doing FOIL. Every once in a while you have to do FOIL, but it's nice when you don't have to. So turn the page, or no, don't turn the page. To the very bottom, preview of factoring. Matthew just mentioned factoring. You've all taken 120 or you tested into here, so you all know how to factor. But it might have been a little while, even winter break, that's like a whole month ago that you were factoring. Or maybe it's been a year or more for you. So we want to think about what is factoring. Well, factoring is just going backwards. So as a preview of what factoring will do, I wanted to show you that it is exactly this sum product shortcut that shows you how to factor a trinomial. So for instance, here I have x squared plus 9x plus 20. What were the two numbers that I must have been using to add together and multiply? 5 and 4, right? 5 plus 4 is 9, and 5 times 4 is 20. Everyone go ahead and write it down. It's really x plus 5 and x plus 4, right? If you look at the trinomial x squared plus 9x plus 20, the two numbers I must have been using were 5 and 4. Could I have written it down like this, x plus 4 and x plus 5?
Yes.
Yeah, and that's fine. That doesn't matter. You can write it down in either order you like, but it must be 4 and 5. Now, are you sure? Are those the only two numbers in the universe that will multiply to make 20 and add to make 9? Maybe there's more. Are there any other numbers that multiply to make 20 and add to make 9? There could be, I guess. Let's just check. If I do a factor table for 20, that is, what are all the numbers that multiply to make 20? It could be 1 times 20, or 2 times 10, or 3 times nothing, or 4 times 5, or 5 times 4, but that's the same fact. And that's it. I don't have to keep going any higher. If I keep checking, 6 doesn't, 7 doesn't, 8 doesn't, 9 doesn't, 10 does, but that would be 10 times 2, and that'd be the same fact. So these are my only facts, right? These are the only whole numbers that multiply to make 20. And which one adds to make 9? Just the 4 and 5. So indeed, it is unique. Okay, it's not like there's going to be lots of different possibilities. You're just going to be able to find the one possibility. Okay, so try another one. Don't shout out the answer. And let's have the right question in our mind. Everyone write out the question. What two numbers multiply to make the last term? To make the last term. That add to make the middle term. All right, that question is very important. When we do factoring in this class, and we're going to do a whole bunch of factoring in this class. In fact, if I were to choose one thing that this whole class is about, probably about factoring. When we factor, you'll always be asking the question, what do you multiply to make the last number that you add to make the middle number? And to help you, I'm probably always going to write out, what do you multiply to make 40 that you add to make 13? I'll put those two little symbols above the numbers to remind you, what am I multiplying to make 40 that I add to make 13? And maybe some of you already figured it out. What do you multiply to make 40 that you add to make 13? 8 and 5. And so that's your answer. It would have been x plus 8 and x plus 5. And that's called factoring. To move from x squared plus 13x plus 40 into x plus 8 times x plus 5, that's called factoring. How about the very last one? What do you multiply to make 42 that you add to make 13?
7 and 6.
Yeah, 7 and 6. So you can write x plus 6, x plus 7. You can write x plus 7, x plus 6. Doesn't matter what order you write it in, just so long as it's the numbers 6 and 7. So what could you say about foiling and factoring? They are, what could you say about them as processes? Like for instance, I take x plus 2 times x minus 7, and that gives me x squared minus 5x minus 14. And then, so that's FOIL, right? I just FOILed it. And then I take that and I factor it back into x plus 2, x minus 7. What can you say about FOIL and factor? They are opposites, right? They're opposites. They're perfect opposites. What is FOIL? What operation is FOIL? What are you technically doing? Distributing, which is multiplication, right? FOIL is multiplication. So what's factoring? It is division. It might not be obvious that it's division yet, but it is division. So that's just some big perspective thought about what we're doing in this class. FOILing is multiplying, factoring is division. They're opposite processes. So you can always check your work by doing the reverse. You know, if you do FOIL and you want to know if you got it right, you can factor, just like Maddie said. Or if you factor something and you want to know if you got it right, you can FOIL it and see if you get back the same answer. All right. Well, very nice, folks. So I think that's the end of my interlude. Yes, it is. So let's go back to our notes packet. And the next few problems are just applications of FOIL. So the first one, 29. Can we do the shortcut called sum product? Can we do the sum product shortcut? Why can't we? Because there's a 2 there, gosh darn it. The sum product rule only worked if it was x plus a number or x plus a number. There's a 2 there, so in fact you will just have to FOIL this. Okay, you cannot apply the shortcut now. So let's go ahead and do it once. So we FOIL 2x times x is 2x squared. And outer 2x times negative 11 is minus 22x. And inner 8 times x is 8x. And last 8 times negative 11 is negative 88. I really recommend that you all are showing those rainbow lines. I call them rainbow lines. That's just what I call them. But I really hope that you're showing your lines so that your eyeballs are seeing the right numbers as you multiply. So then we combine like terms. I always underline my like terms. And what do we get? Did I get that right? Is that really it? Yeah, that looks like it. Okay, well, looking at this, can we now factor it by saying what multiplies to make 88 that adds to make 14? No, unfortunately, because there's that 2 up front. So those 2 shortcuts that we were just talking about only works if it's x plus something and x plus something. Right now, there's a 2 up front, so we can't FOIL this as it is. Okay, but I'm getting a little ahead of myself. We have a whole chapter devoted to factoring. Let's just keep going and talk about multiplication. Everybody go ahead and FOIL this one. This is a genuine FOIL problem. You can't just do the sum product rule because the x has a 5 on it. So go ahead and FOIL it out and see what you get. I like that some of you guys are checking your answer in the back. You can always check your answer in the back of the packet to see if you got it. And if not, you go back and look for your mistake. So FOIL, do I need to rewrite this so that it's x minus 9 first? Do we need to put those terms in order? No, you don't have to. It'll all work out in the end. So we'll go ahead and FOIL. So negative 45x, and then outer plus 18, and then inner plus 5x squared, and then last minus 2x. So now they're all out of order. We have to put them in the right order. 5x squared minus 47x plus 18. Did anyone else get that? Okay, good, good. Okay, I think that's it then. Was that the answer in the back, Lilia?
Yeah.
Okay, good. All right. So that's classic FOIL. And moving on to section 5.4. So we still have about 20 minutes left of class. It's okay if we go beyond what we said we'd do today. That's good. We'll just get a little ahead. So let's go ahead and get a little ahead. Section 5.4, what are we doing in section 5.4? Yeah, in this case, we are squaring a binomial. That would be your vocabulary. You're going to square a binomial. Now, do we know how to square a binomial? How do you square anything? Multiply it times itself, right? Now, just to point out, what you're not allowed to do, and this is one of the most common mistakes, what you're not allowed to do is just square both of them. You can't just write down n squared plus 9. Okay, that would be incorrect. Why is that incorrect? Because the parenthesis is there. You have to go with the definition of exponentiation. The definition, write this down, is n plus 3 times n plus 3. That's the definition, right? Because when you square something, you multiply it times itself. So you have to always use the definition. So in that case, now we FOIL it. Can we use the shortcut of sum product? Yeah, we can, because it's just a variable plus or minus a number, a variable plus or minus a number. So the answer is n squared plus the sum, which is 6n plus the product, which is 9. What's the difference between the right answer and the incorrect intuitive answer? It's missing the middle term, isn't it? So just going with the intuition, which is incorrect, you're missing out on the middle term, and that's why it's wrong. This process, if you just square the first and the last, that would technically be called full, right? Because you're skipping out on the OA part, the outer and the inner term. All right. Well, so that's how you square a binomial. How would you square this binomial? What would I write down? Oh, wait, I can't. Vanessa.
W squared, and then
Oh, just tell me what to write down first by definition. W minus 12 squared means? What?
times W.
Yeah, exactly. Folks, always just start by writing down what squared means. Squared just means multiply it times itself. And then at that point, yes, Vanessa, you could do the rule, or the sum product rule, and what's your final answer, Vanessa?
So W squared minus 1 squared W.
Yeah, exactly. That was the sum product rule. Yeah, very good. Okay, well that's nice and convenient whenever it is just a variable and a number. What about this next one, 33, 8a minus 9? Can you just use the sum product rule? No, because there's an 8 on the a. So you will just have to FOIL this out yourself. So I'm not going to do this one with you. You started out by just writing 8a minus 9 times 8a minus 9, and then you do FOIL, and then you combine like terms and you get your answer. So I'm going to leave 33 and 34 for you to do, for you to practice, and you can always check the answer in the back of the packet. And otherwise, let's keep going. Now, that whole page that we just finished, this here, we were squaring a binomial. So again, if anybody said, hey, what is this problem? You would say, oh, squaring that binomial, right? That's what you're technically doing, squaring a binomial. So on the next page, what are we doing? Are we squaring a binomial on the next page? No. And yet they do seem pretty similar to each other. What do you notice about all of these problems? What do they all have in common? Yeah, they're the same expression, but one is plus and one is minus. Does everyone agree? It's an x and a 5, but one's plus, one minus. They're both 4p and 1, but one's plus, one minus. They're both x and 5/7, but one is plus and one is minus. And they're both 11y squared and 3, but one's plus and one is minus. So that's a pattern. It kind of stands out, and it begs the question, what's going to happen? Like, what's going to happen? That seems kind of special, that one is plus and one is minus. So first, let's all identify the vocabulary right up at the top here, we're wondering what's going to happen anytime you multiply a plus b times a minus b.
Meaning same numbers, different signs.
The next thing I want you to know is that these two binomials are called conjugates.
We get conjugates. Anytime two binomials are the same, except one is plus and one is minus, they're called conjugates. So what we're doing in all four of these problems, we are multiplying conjugates. So I'm going to give you a formula for what happens when you multiply conjugates. But before we do, let's go ahead and do a couple and see if we can guess what the formula is. So what happens when you FOIL x plus 5 times x minus 5? First of all, can you use the sum product rule?
Yeah, you sure can. So x squared, what's the sum? 5 plus negative 5? 0x, and the product? Negative 25. Now, do we have to write 0x? No, you don't really. And so what can we write it down as? Yeah, x squared minus 25. Let's try that again. Let's do 4p plus 1 times 4p minus 1. Can we do the sum product rule? No, because the 4 on the p. So instead you just FOIL it out. You get to do FOIL. So let's see. First, that would be 16p squared outer minus 4p inner plus 4p and last minus 1. So what happens? Yeah, what happens to the middle two terms when you combine like terms? Yeah, they cancel, which once again gives us the 16p squared plus 0p minus 1. But again, do we have to write 0p? No, we can just write down 16p squared minus 1. Now look again at the one we just did a second ago, the x squared plus 0x minus 25. What do you suppose happened where that 0x was? Instead of doing the shortcut, had you actually done FOIL, what would you have seen? Yeah, you'd have seen cancellation terms, right? X squared, and then it would have been a minus 5x, and then a plus 5x, and then a minus 25. And you would have seen those two middle terms cancel out to give you the 0x. We didn't see it because we did the shortcut. But now we can probably all take a guess as to what's about to happen when we multiply these conjugates. What will happen to the middle terms? They'll cancel out. What's the middle term of FOIL? The ui, right? The ui is going to cancel out. And what you're really left with is just full. So if we were to do FOIL, it would be x squared, and then the outer term would be minus 5/7 x, and the inner term would be plus 5/7 x. And then the last term would be, ooh, what's 5/7 times 5/7? What is 5/7 times 5/7? 25/49, right? And just to remind ourselves, 5/7 times 5/7 is 5/7 squared. And how do you square a fraction? You square the numerator and denominator separately, which still gives you 25/49, right? Okay, so that gives us minus 25/49. And again, those middle terms canceled out, and we just had x squared minus 25/49. So if we were to go back and ask the question, what happens when you multiply conjugates? What's one answer you can give? What happens when you multiply conjugates? Yeah, say it again, Dana. The middle terms cancel out, right? And you're just left with the first and the last terms. So everyone go ahead and try the last one, number 38. Go ahead and FOIL all that together. If you'd like, you can try to guess what the answer is without doing all that work. We've got 5 minutes. I'll start wrapping up. Yeah, since you know it's a conjugate, you might just try guessing. What if you just multiply the first and then just multiply the last? Of course, that's a shortcut. I don't want to imply that I'm all about shortcuts. I do like shortcuts. But it's important that you always go back to the definition of first, outer, inner, last. But if you did just do the firsts, 11 times 11 is 121, so that'd be 121. What's y squared times y squared? Yeah, you add 2 plus 2 is 4, so 121 minus 4. And then I know that the inner and outer terms are going to cancel because I'm multiplying conjugates, so now I just go to the last, and negative 3 times 3 is minus 9. Okay. One more thing, let's go back up and finish our notes. Up at the top it said, what is a plus b times a minus b? So we can all go ahead and calculate that now. What is a plus b times a minus b? If you do full FOIL, it'd be first a squared, outer negative ab, right, because it's a times b, but it's negative. Inner positive b times a, which is still a times b. And then last, positive times a negative b, so that's minus b squared. And what happens to the middle terms, ab? You have a negative ab and a positive ab, they cancel out. And the answer is a squared minus b squared. So jot that in on your notes. That you have a plus b times a minus b is a squared minus b squared. And essentially, this is what section 5.4 is about. It's about looking at patterns. So 5.4 started by squaring a binomial. That means foiling when they're the same. And then we did FOIL when they're conjugates. And then we'll keep on, oh no, that's actually it for 5.4. Goody. Okay, your midway quiz. I'm sure you're all chomping at the bit. So your midway quiz, it is very short. It's just one page on the front. Keep in mind, you need to show work. Show any work at all. Even if it's just a matter of showing what definition you used. You want to show some sort of work for every problem to justify why you chose the answer that you did. Now, folks, you all heard me say that you can use your textbook or your notes, but not Google and not another human. Here's a question. Can you email me? Can you come to my office or email me? Sure you can. I'm the teacher. You can always come ask me a question because I will answer the question for you in a way that's not giving away the answer. It still requires you to do the work. But by all means, if you're sitting there looking at your quiz and you feel, oh no, I don't know what this means, you can just email me or come to my office and I would be more than happy to help clarify what the question means without giving anything away that I wouldn't tell anyone. So just keep that in mind. This quiz is due when? Wednesday. Yeah, Wednesday, next class. Did everyone already bring up a student info sheet and syllabus quiz? You can all bring it up here and drop it off. Well, my goodness, does anyone have any questions? It's 2:48. I'm not letting you go early, but I have nothing else to say. Yep. Yeah, I can't stop you from leaving, folks, but I'm not letting you go early. I'm not letting you go early. But if you have to go, I understand. No, seriously, I'm not letting you go early. I can't stop you from leaving. If anyone has any questions, come on up and ask me. I'm right here.